Vector Vj is really what we call this orthogonal, the Schmidt process of orthonormalization actually. So Aj minus sum that goes from I equal to 1 to j minus 1. So if you have j, you will go up to j minus 1 or ij aj. Okay, so these are the two ways. While rjj is really take your vj's. So if you have these two, you can compute rj and you can compute what you call qj's as well. So rjj is going to be that take your vector vj and take your vector vj, okay, and compute its magnitude. And you can see it actually. So you can see it, that we have seen this, that r22 is really this vector v2 and its magnitude. R33 is this vector v3 and its magnitude actually. So rjj is going to be what we call magnitude vj. And the qj, if you want to compute qj, so the qj is really vj divided by the magnitude of it. So the vj, vector vj divided by the rjj, in other words the magnitude of vj. So this is the algorithm of the QR factorization when your entries are complex actually. So this is very much analog to what you have here actually. Okay, the only difference is that now you have a bit different in a product actually. You have a bit different scalar product, okay, according to set of complex numbers. So that's what is really the QR factorization. What are some of the benefits of say QR factorization? Okay, what are some of the benefits? So there are lots of benefits. We will see more in the future. But one of the key benefit that you have for the QR factorization is really that it gives you a kind of a really stable method for solving a system of equation, a consistent system of equation actually. Okay, a consistent system of equation. But it's expensive than other methods. Okay, so it's computationally expensive because you need to do a lot of computations. Okay, so if you, for example, take if you, for example, so what is an application of QR factorization? Application of QR factorization actually. Okay, so you can see that how unitary matrices are really deeply rooted in different kind of theories. So imagine you have a system Ax equal to b that you want to solve. Now, I know that I can factorize matrix A in the terms of Q R actually equal to B. And I know that Q is our orthogonal matrix, so I can take, for example, Q transpose and multiply in both, or the Q star and multiply onto the both sides. So Rx equal to Q star B. Okay, so if you are talking about real numbers, it's going to be transpose, Q star is going to be transpose, and if you are talking about matrix of the complex numbers, this Q star is going to be the conjugate transpose actually, so the Q star B. And I know that since Q is unitary, so the Q star dot Q is going to be identity. So this is going to be true if Rx equal to Q star B. Okay? So you can turn a complicated system of equation into this actually. Now why this is really easy to compute? So this is really a triangular system actually. So so there is a specific term for it, that this is a triangular system. So if I call this, for example, product y, then this Rx equal to y is really a triangular system actually, in which you can do the backward substitution. The last entry of this system would be very easy to compute actually, because that would be something like, okay, 2x equal to 3, and then using that, you know, last entry, you can compute using the last entry is going to be like a simple equation in one variable. Then the equation above is going to involve two variables in which one is known, so you can compute other, and the third equation is going to involve three variables, okay, in which you know the two variables, so you can compute other. So it's going to be really simple triangular system actually, okay, a really simple triangular system. But for this, obviously, you need to first factorize the system into the QR. Then you can compute the solution X of it actually. But factorization is an expensive process actually, computationally, if you want to do that. So factorization is an expensive process computationally. Okay.